A function f is said to be a polynomial function of degree n in one variable if it can be written in the form f of x equals an x to the n plus an minus 1 x to the n minus 1 plus dot dot dot, which means this pattern continues, plus a1x plus a0. The constants here that are multiplied by the powers of x are real numbers, and the first one, the coefficient of the largest power of x, should not be 0. Otherwise, then it will not be a polynomial of degree n, but rather whatever the first coefficient, which is not 0, and the associated power. So notice that the degree of a term in a polynomial is simply the exponent of the variable, and so that means this is an nth degree term, this is an n minus 1th degree term, this is a first degree term, and remember that the a0 can be written as a0 times x to the 0, because as we all know, the 0th power of x is just 1. So notice how this is written in descending order of powers from n all the way to 0, and the degree of the polynomial itself is the same as the degree of the highest degree term in it, okay? And again, the numbers that are multiplied by the powers of x are called coefficients, and the coefficient of the highest degree term is called the lead coefficient. Some polynomial functions are referred to using special names as depicted in this table, and for higher degree polynomials we usually just say nth degree polynomial, such as 6th degree polynomial, 7th degree polynomial, etc. So in the first row here we have a constant function. Notice there is no variable here, just a constant. The only variable you can think of being there is the 0th power of the variable x. But of course, notice that we are using x here for simplicity and out of habit, but you could have used any letter you wanted for the variable x. So there's nothing necessarily special about the variable x. Now, as you can see, the degree of this polynomial is just the exponent of the variable, so therefore it's 0. So a constant function is a 0 degree polynomial, and the lead coefficient is the only coefficient there is, which is 5. In the next one, we see a linear function because the highest degree term in it has degree 1. So it's a first degree polynomial, and the lead coefficient, which is the coefficient of the highest degree term, is obviously 4. The next function is a quadratic function, the kind we're going to look at very closely today. So you can see the highest degree term is x squared, then we have negative 9x, then we have negative 7. This is a second degree term, this is a first degree term, this is a 0 degree term. So the degree of the whole polynomial, which is the same as the degree of its highest degree term, is going to be 2. The lead coefficient is invisible, but it's there, it's a 1, okay? For the next one, we have a cubic function, which is a third degree basically polynomial, and the lead coefficient is obviously 1/2. Notice that we have written all these polynomials in descending order of powers. This polynomial has 1, 2, 3, 4 terms, etc. So the lead coefficient is the coefficient of the highest power, which is x cubed, so it's 1/2. In the next one, we have a 4th degree function, also known as a quartic function, and notice that here the lead coefficient is 1, and the degree, of course, is 4. In the next one, which is called a quintic function, it's a 5th degree polynomial, and the lead coefficient is 1. Here we take a look at the graph of some of these functions. Notice that a constant function the value of the output y, which is the same as f of x, never changes. It's always the same. Here we have 5, so we end up as the graph of such a function with just a horizontal line going through y equals 5. So notice for the domain of such a function, we would have all real numbers, right? And for the range of this function, a very limited range, there's only one output, so it's just a single number, 5. The only y value that is available for the outputs of this function. Next, we have a linear function, f of x equals 4x minus 3. Here, of course, the degree is the exponent of the variable 1, and the lead coefficient is 4. And here's a graph of the linear function, which we're all too familiar with. Here we have a quadratic function. This is the kind of function we're going to focus on today, as previously mentioned. F of x equals x squared minus x minus 7. Degree is, of course, 2, and the lead coefficient here is 1. The shape of this graph, as we know, is called a parabola, and we're going to learn a whole lot about graphing such functions today. Here we have a cubic function, 1/2 x cubed plus square root of 5x minus 2x minus 1. The degree is 3. The lead coefficient is 1/2. Notice that regardless of the power, these are all very well-behaved functions. That's true about all polynomials. They are continuous, they have no gaps, and they're smooth. You don't see any sharp edges when it comes to polynomials. All nice round type of turns, etc. Smooth turns with no sharp corners. Not necessarily fully round or anything like that, just in the sense of being smooth. Here's a 4th degree polynomial, and we call these quadratic functions, and the degree here is, of course, 4, and the lead coefficient is 1. Here's a quintic function with a degree 5 and a lead coefficient 1. We saw this before as our examples. Now we're going to actually learn how to graph these functions. That looks pretty complex and elaborate, but once you really learn a few basic facts, they become quite easy to graph. So we'll go ahead and learn that throughout this term. Now we want to get back to the main topic of the day, which is we're going to focus on 2nd degree polynomial functions. And as we know, they're called quadratic functions, and they can be written as f of x equals ax squared plus bx plus c, with a, b, and c being real coefficients, and a, of course, should not be 0, because otherwise this term collapses and we break down to a linear equation. So we want to maintain the quadratic form. We have to make sure that the coefficient of the quadratic term is not 0. This form of a quadratic function is called the standard form, and it's very helpful for categorization purposes. It's not the most useful form. Just like, for example, when we were studying lines, we have ax plus by equals c was the standard linear form, and it was good for categorization purposes, but not necessarily the most useful form. That was the slope-intercept form, which immediately told us a lot of useful information about a line. The reference or the base quadratic function is f of x equals x squared. When we talk about other parabolas or quadratic functions, we want to usually compare them to this reference quadratic function. Here you can see this can be graphed quite easily. Now we know that since changing x with negative x doesn't change the equation, because if you can see we have y equals x squared. If we change x with negative x, we get y equals quantity negative x squared. which is back to y equals x squared. Since changing x and negative x doesn't change the original equation, we know this is going to have symmetry with respect to the y-axis. And this line right here, in fact, the y-axis itself is the what's called the axis of symmetry for this particular parabola. The domain is all real numbers. There's no real number you can't plug into this expression. And notice the range, though, is going to get limited to all non-negative real numbers, because we're not going to have, when you plug in real numbers into x squared, you're not going to get any negative outputs. So the outputs are all going to be 0 or higher. That's why the range is bracket 0, comma infinity, or the half open interval 0 to infinity. As already mentioned, the name of the shape representing the graph of a quadratic function is called a parabola. It is symmetric with respect to its axis of symmetry. In this particular case, the y-axis itself is the axis of symmetry. And of course, as we know, the equation of the y-axis is simply x equals 0, because for every point on the y-axis, the x value is 0, regardless of the corresponding y value. Now, every quadratic function in standard form ax squared plus bx plus c can, through algebraic manipulation, be put in another form called the vertex form. This is, in fact, the most useful form of a quadratic function, because when you have this form, it ends up that turns out that the vertex of the parabola, which is either the highest point or the lowest point of the parabola, is going to be at the point hk in this form. Okay, so this is a form we're going to get very, very comfortable with today. All right, so this form, the vertex form, has a wealth of information in it, but primarily the fact that x equals h is the axis of symmetry, hk is the vertex, as we've already mentioned. Now, if h is greater than 0, the graph of the function f of x equals x squared, which is our reference function, would have been shifted h units to the right. And if h is negative, then it would have been shifted absolute value of h units to the left. If k is positive, that means the original or reference y equals x squared function has been vertically shifted k units upward. And this one, if k is negative, then it would have been vertically shifted absolute value of k units downward. This, of course, is consistent with all the rules of transformations of functions that we have learned about already. Now, A itself gives us some very useful information about the parabola. If A is positive, the parabola is going to be opening up like that, okay? It's like the happy face, right? So if A is negative, it opens down like so, so kind of like the sad face, right? If the absolute value of A is greater than 1, that means it's going to be vertically stretched, which means horizontally shrunk, so it's going to be narrower than f of x equals x squared. Remember that a vertical stretch goes hand in hand with a horizontal shrinking, right, or a horizontal compression. So it's going. So when the absolute value of this coefficient is greater than 1, the parabola is going to be narrower than y equals x squared. If the absolute value of a is 1, then it's going to be the same width as the graph of f of x equals x squared, just shifted around according to h and k. And when the absolute value of a is a fraction between 0 and 1, then it's going to be vertically compressed, which means horizontally stretched. So it's going to be wider than y equals x squared or f of x equals x squared. So you can see how much information is contained in this vertex form of a quadratic function. Here we take a look at some horizontal translations or shifts of the graph of y equals x squared. Remember that once you have the graph of x squared, which is shown here in red, then to get the graph of y equals x minus 1, quantity x minus 1 squared, you're going to pick that up and lift it and shift it 1 unit to the right. So think of it like this. Whatever happens to x squared happens to quantity x minus 1 squared 1 unit later, okay? And this one, you have y equals x plus 1 squared. Notice that whatever happens to the red function happens to the blue function here, quantity x plus 1 squared, 1 unit earlier, right? Think of it that way. That's kind of a nice way of remembering that. And it's consistent again with the transformations we have learned about, the transformations of functions. Now, to get a quick graph of a quadratic function with some actual points you can plot, here's what you do. Go ahead and locate the vertex first. Let's look at this middle one first, the base reference function, right? We know that we can write it as y equals 1 times x minus 0 squared plus 0, right? So we know that a is 1, h is 0, and k is 0. So the vertex is at hk, so it's at 0, 0. The axis of symmetry is x equals h, which is x equals 0. And we know the domain is all reals, and the range is all non-negative reals, right? So once you know where the vertex is, go ahead and start with that, and then move 1 unit to the left of x equals 0. So that takes you to x equals negative 1, and 1 unit to the right of it. So that takes you to x equals 1. Now, notice that when you plug in negative 1, you get y equals quantity negative 1 squared, which gives you 1. When you plug in 1, that gives you 1 squared, which is 1. So these 3 points are all that you need to graph this parabola uniquely, okay? Now, so here's 0, 0, here's negative 1, 1, and here is 1, 1. Then we just smoothly graph the parabola that goes through it. Notice the same goes here. For example, with this one, we know that we can write this as 1 times, if we want to write x plus 1 squared as a difference so that it's in h minus k, x minus h squared format, we would write it as x minus negative 1 squared plus 0, right? So h here is what comes after the minus sign. So it's going to be negative 1, and k is 0. So the vertex is at negative 1, 0. So we start there. Then we move 1 unit to the left of negative 1, which is negative 2, and move 1 unit to the right. Because of symmetry, these are going to be perfect points for graphing this parabola. So you can see here is negative 2, 1 from the table. Here is negative 1, 0 right here. And here is 0, 1 right there. So we plot those, and then we smoothly connect them using this graph right here. And for x minus 1 squared, remember that we can write it as 1 times x minus 1 squared plus 0. So a is 1, h is 1, and k is 0. So the vertex is at hk, so 1, 0. The axis of symmetry is x equals 1. See, it goes right there, x equals 1. that vertical line that goes through 1. For this one, the axis of symmetry was x equals -1. So it's that vertical line right there. All right, now remember, the axis of symmetry is not part of the graph itself, but it's a nice thing to draw, perhaps in dashed format, which will show you what the line of reflection is between the left and right part of this kind of a parabola. Notice again, for all three of them, the domain is the same, all reals, and none of them have a negative output, so all ranges are all non-negative reals, right? So from 0 to infinity. All right, so here's an example for horizontal shifts of the graph of y equals x squared. Now we'll take a look at some vertical translations or shifts of the graph of y equals x squared. Remember, starting with y equals x squared, which is shown here in red, you want to graph y equals x squared plus 1. You're just going to add 1 to all y values. So you're going to just pull the graph up 1 unit. For x squared minus 1, you're just going to pull the graph down 1 unit. So you end up with the green and the blue curve that we see. For the graph, you do exactly the same as we did before. Start with the vertex, then plot 1 point to the left of the vertex's x value and 1 point to the right. And then you have 3 points which you can plot and quickly graph your parabola. So for this one, notice we can write it as 1 times x minus 0 squared plus -1. So h is 0, k is -1. So the vertex is going to be at 0, -1. The axis of symmetry is x equals h, so x equals 0, and there is the domain and the range. Notice that the range changes here because for this blue function that we were looking at just now, notice that all the outputs are going to start at -1 and go above that. So that's why the range is -1 to infinity. For the green one, notice the range is going to be all real numbers that are greater than or equal to 1. That's why you end up with 1 to infinity. They all have the same axis of symmetry, and that's about it. They have different vertices, of course, and different ranges. That's about the only thing that's different about them, right? All right, next we'll look at some vertical stretches, which is similar to horizontal shrinking, and vertical shrinking, which is simultaneous with a horizontal stretch of y equals x squared. So here is y equals x squared in red. So remember, if the absolute value of a is greater than 1, the parabola is going to be narrower than y equals x squared because it's going to be vertically stretched, which translates into horizontally shrunk. Now, if the absolute value of a is between 0 and 1, such as when y equals 1/2 x squared, remember that it's going to be wider than y equals x squared because it's going to be vertically shrunk, which translates into horizontally expanded or stretched, right? All right, so all of them, of course, are going to have the same domain and range, right? Domain being all reals, range being all non-negative reals. They all have the same axis of symmetry. H equals 0 for all of them. So x equals 0 is going to be the axis of symmetry for all of them. And there you have it. To graph them, do exactly the same as before. Once you know what the vertex, like look at 1/2 x squared. Once you know what the vertex is, then go 1 unit to the left, 1 unit to the right, plot those. There you go. You have a nice graph right there. Same with x squared and 2x squared, of course. So for 2x squared, there is the vertex. I go 1 unit to the left and 1 unit to the right of the x coordinate of the vertex. I plug in and get the y values. When I plug in -1 here, I get the square of -1 is 1 times 2 is 2. And for 1, I get the same result. So there are the 3 points, -1, 2, 0, 0, and 1, 2, which you smoothly connect to get the graph of 2x squared. Next, we want to take a look at a vertical reflection of the graph of y equals x squared. Remember that if you have the graph of f of x, then to get the graph of negative f of x, you're going to basically vertically reflect the graph of f of x with respect to the x-axis. And that's how you end up with the blue function here for negative x squared. And that's basically because any y value for a given point on this graph is going to be multiplied by -1, so it's just going to jump down here. All right, so notice we can write this as 1 times x minus 0 squared plus 0. So the h and k are both 0. The vertex is at 0, 0. A is 1, so it's going to have the same width as the graph of x squared. Obviously, this is our standard base graph, so we knew all that, right? For this one, notice that the absolute value of a is going to be 1, so it's going to be the exact same width as the graph of x squared. And hk are 0, so the vertex is at 0, 0. Axis of symmetry is x equals 0, as is, of course, for the base function. Their domain and range, the domains are the same, of course, because any value of x can be plugged into either x squared or negative x squared. Ranges are very different because when it comes to y equals x squared, the range is going to be all non-negative real numbers. When it comes to the graph of y equals negative x squared, the range is going to be the set of all non-positive real numbers, meaning 0 or anything lower than that. That's, of course, because when you plug in any real number into this expression, negative x squared, the output is going to be 0 or some negative number, because this part will be either 0 or positive, so the opposite of that will be 0 or negative. And that's how you end up with this particular graph. As far as getting some actual numbers you can plug in, again, start with the vertex, right, in both cases, then go 1 unit to the left and 1 unit to the right, plug those in, get your y values, and you have the 3 points you need to graph either function. Next, we want to look at mixed transformations. Look at this function, for example. If we start with the graph of x squared, notice we're going to be moving it 3 units to the right, 4 units up, and we're going to vertically stretch it by a factor of 2. Now, that vertical stretch is going to translate into a horizontal shrinking, right? So we're not surprised that there's going to be a visual appearance of shrinking, even though we're actually vertically stretching the graph of y equals x squared. And that's, of course, normal. Now, notice that the absolute value of a is greater than 1, so we expect that this parabola to be narrower than y equals x squared. And that's how you can obtain the graph by just applying transformations. But if you actually want to get 3 strategic points to plot, always start with the vertex, which we know is 3, 4. Move 1 unit to the left of the x value of the vertex and 1 unit to the right. Plug in and obtain your y values, then plug those in and you have your graph. Notice that the domain, of course, for all polynomial functions is all real numbers. The range here is going to be different because we're not going to have any output below this line, which is y equals 4. That's why our range is the set of all real numbers greater than or equal to 4, or the half open interval 4 to infinity. Here's another example with mixed transformations. So notice, to get the graph of this from the graph of x squared, we would move the graph of x squared 1 unit to the left. Remember, when this is positive 1, you actually move to the left. Then 3 units down, and we're going to vertically compress it by a factor of negative 1/2. Now notice that that actually translates into a horizontal stretch, right? Now notice that x equals negative 1 is going to be the line of symmetry here. And as far as the domain is concerned, it's of course all reals. The range is not going to include any y value greater than negative 3, right? So that's why we know the range is going to be negative infinity all the way up to negative 3 and including negative 3. That's why we need a bracket, right? Now notice that the absolute value of a is between 0 and 1, so we knew this parabola should be wider than y equals x squared. And that's it. So you can see how much information is hidden inside this form. Okay, so here we have a quadratic function which is given in standard form, and we want to graph it by first writing it in vertex form and then naming the transformations needed to graph the function. Transformations needed to the graph of y equals x squared to graph to obtain the graph of this function. So here what we'll do, the first thing we'll do is we'll replace f of x with y. It'll make it easier to work with the equation. All right, so notice that we do want to obviously move toward this form, right? So what we're going to do is we're going to go ahead and complete the square on x squared plus 6x. Now, if the coefficient here were not 1, then we would temporarily divide it off and then multiply it back in at the end. That's the easiest way to deal with that. All right, so remember we take half the coefficient of x, which is 6, that gives us 3, and then we square that to find out what we need to add to complete the square. Now, in order to keep the balance, I'm going to go ahead and subtract 9 right away. And don't forget, we already have a plus 11, right? So notice x squared plus 6x and x squared plus 6x plus 9 minus 9 are the exact same thing because 9 minus 9 is 0. But they do look different enough to help us find this perfect square trinomial. So that's going to be y equals quantity x plus 3 squared. Now, negative 9 plus 11, that's positive 2. So there we have it. We just put that particular quadratic function into vertex form, right? So notice that the vertex here is going to be at negative 3, 2. The axis of symmetry, don't forget, if it's plus 3 here, that means h is actually what? Negative 3. So the axis of symmetry is going to have equation x equals negative 3. Now, to get this graph from the graph of y equals x squared, so move the graph of y equals x squared 3 units to the left, or you can say leftward, and 2 units upward. Now, no vertical shrinking or stretching is necessary because a right here, invisible, is 1. So it has the same width as the graph of x squared, right? So those are the transformations you would need. But let's also go ahead and find some points. Remember, we're going to start with the vertex in the middle. We'll move 1 unit to the left of that, so that's -4, and 1 unit to the right of -3, which is -2. Now, when I plug in -4 in here, I get -4 plus 3, which is -1. When I square that, I get 1. When I add 2, I get 3. I'll do the same for -2 to make sure I also get 3. -2 plus 3, that's 1. Squared is 1, plus 2 is 3. So those are 3 points we can use to get a really nice graph. And let's go ahead and do a quick sketch. So -4, 1, 2, 3, 4, 3, 1, 2, 3, -3, so -3, 1, 2. Make sure you don't deprive yourself of the ability to do this by hand, and don't just rely on technology. So you go 1, 2, 3. We will definitely learn how to use technology, but only after we actually learn and understand how this should be done by hand, because that's where the real understanding lies, right? So that actually did not come out nicely. Let me try it one more time. All right, so we'll do the cup first, and then we'll go up like that. Now, here's a graph of the axis of symmetry right there. All right, so the equation of the axis of symmetry is, remember, x equals -3. Now, what is the domain for this function? Of course, it's a polynomial. It's always all reals. There is no number you can plug into a polynomial to get you in trouble. The range, though, notice we don't have any. Let's mark the points. This was the vertex was at -3, 2. This point on the left was -4, 3. And the point on the right was -2, 3. So notice there's not going to be any output below the line y equals -3. So the range is going to be bracket -3 to infinity. Include the -3 in your range. So that's why we need a bracket, not a parentheses. All right, so where is this function decreasing? Well, notice it's decreasing on -infinity all the way to -3, right? So decreasing on -infinity to 3. Always give those intervals as open intervals for decreasing, increasing, etc. And it is increasing on -3 to infinity. And that's how that is done. Okay. And that should do it for us. Okay, so make sure you understand that, and we'll proceed. All right, so we're going to do everything we just did for the previous problem for this problem as well. So once again, we'll go ahead and replace f of x with y. So we end up with y equals -3x squared plus 12x minus 16. Now, different textbooks show you different ways of handling this, but I'm going to show you a easy way to handle it, which most textbooks do not actually cover. So rather than, this is the way a lot of textbooks have you do it. Factor out a -3 and then complete the square within the parentheses. Because remember, to complete the square, you need this coefficient to be 1, right? So there's an easier way. Here's what we'll do. We'll temporarily go ahead and divide off the -3. So divide both sides by -3. So we get y over -3 equals, remember, that's going to mean dividing each of these terms by negative 3, right? Because on the right side, they're going to get split up like that, right? So we end up with, on the right side, x squared minus 4x, right? Plus 16 over 3. So now we're going to complete the square on those two terms. So we're going to take 1/2 of negative 4, which is negative 2, and we're going to square that to get 4. So we get y over negative 3 equals x squared minus 4x. We need to add a 4. And right away, we'll go ahead and subtract the 4. And don't forget, we still have plus 16 over 3. So we're going to group those together for a perfect square trinomial, and we'll group those together for a constant. So we get y over negative 3 equals quantity x minus 2 squared. And these two right here, in order to combine them, we need a common denominator. So that's 4 over 1. So we need to go ahead and multiply that top and bottom by 3. So we end up with, let's do that on the side. So we end up with negative 12 plus 16 over 3, right? So what is that? So that's plus 4/3. Like so, okay? Now that we are almost in the form that we want, we're finished with this dividing by negative 3 business. That served its purpose. Now we need to multiply it back in so that we do end up in this form. Okay, so go ahead and multiply both sides by negative 3. So you end up with y equals negative 3 times x minus 2 squared. And what is negative 3 times 4/3? Well, the 3's will cancel out, right? But you end up with what? Negative 4. So minus 4. Remember, this is all down here. That's all scratch work. It's not part of the flow of the problem, right? All right. So we get y equals negative 3 times quantity x minus 2 squared minus 4. Right away, we can see that the vertex is at 2, negative 4. Remember, since this is x minus 2, then h is just 2 itself, right? So, and we get the axis of symmetry is going to be have equation x equals 2. And notice, as far as transformations are concerned, you would have to take the graph of y equals x squared, move it 2 units rightward. That means to the right. 4 units downward, right? Then you're going to vertically stretch it by a factor of 3. And finally, you're going to reflect it. Across the x-axis, okay, because of the minus there. All right. However, the much easier thing to do, since you have it in vertex form, is to just get 3 points very quickly. So we can get those 3 points. Remember, we start with the vertex, which is at 2, negative 4. move 1 unit to the left of x equals 2, that takes us to 1. 1 unit to the right, that takes us to 3. Now, when I plug in 1, I get 1 minus 2 is negative 1. The square of that is 1 times negative 3 is negative 3 minus 4 is negative 7. And when I take 3 and plug it in, I get 3 minus 2 is 1 squared is 1 times negative 3 is negative 3 minus 4 is negative 7, as expected. But we always do it to make sure. Let me shrink this stuff so I can open some space. All right, it's kind of nice we can do that with these virtual whiteboards. You can't do it on the real whiteboard. Okay, so as you can see, we're ready to graph this. So 1, negative 7. Let me actually move it up a little bit because it's going to be mostly below the x-axis, right? So I don't need all that stuff above the x-axis. So 1, and then 1, 2, 3, 4, 5, 6, 7. 1, negative 7. 2, negative 4. So 2, and then 1, 2, 3, 4. Those dots, of course, just to help me graph it, right? They're not actually part of the graph. These dots I'm talking about, okay? The big dots that I'm making darker are part of the graph. And then 3, negative 7. I already know negative 7 is about here. So then I just draw my parabola. All right. All right, so because the absolute value of a was greater than 1, we knew it's going to be narrower than y equals x squared. We expected that. Here's the graph of the axis of symmetry. So what is the equation of the axis of symmetry? Well, x equals what? 2. And the vertex, of course, is at 2, negative 4. Notice that it's increasing on negative infinity all the way up to 2. It's decreasing on every place after that, 2 to infinity. Domain, as with all polynomials, is negative infinity to infinity. The range, which is the outputs, notice you can plug in any x value that you want in this expression, but you're not going to come up with every y value. The y values you come up with are limited to all those below this line right here, which is at y equals negative 4. So the range is going to have all numbers from negative infinity up to negative 4. So all y values less than or equal to negative 4. If you were to write that in set builder notation, it would be all y such that y is less than or equal to negative 4, like so. Okay? So there is all the information we were asked to find for this one. This trick of just plotting the vertex and then one to the left, one to the right is really a simple, beautiful trick that will help you graph it. When you use a system like my math lab or any similar homework system, they're going to want you to provide the vertex and just one point. But when we graph it by hand, we're always going to do one on the left, one on the right of the vertex, so that we make sure we haven't made some kind of a mistake. We make sure those two numbers match. We know they should match. We just want to make sure that they, in fact, do match. All right, so that is how you graph that one. So this trick of dividing both sides by the coefficient of x squared, if it's anything other than 1, is a really efficient and simple trick for not having to deal with more complex algebra later. Make sure you can handle this, and we'll proceed. All right, next we want to talk about the intercepts of a parabola. Now, every up-down parabola, the ones we've been looking at, will, because there are some left-right parabolas that we will study as well. But every up-down parabola will cross the y-axis when x equals 0. If we make x equals 0 in this equation right here, then we get y equals, remember, that's going to zero out, that's going to zero out, so you get y equals c. That's why 0c is the point at which every parabola with equation y equals ax squared plus bx plus c will cross the y-axis. We call 0c the y-intercept of the parabola with equation y equals ax squared plus bx plus c. To find the y-intercept of any parabola, we simply set x equals 0 and then solve for y. Now, not every parabola, however, crosses the x-axis. Let me show you some examples. See, here's a parabola. Is that parabola ever going to cross the x-axis? It's not. So not every parabola is going to have an x-intercept. They will all have a single y-intercept, but some will not have any x-intercepts. Here's another one here. See, that one won't cross the x-axis either. Some parabolas cross the x-axis twice, like so, okay? Some will cross it only once. Let me get rid of these and do that one for you. Consider this one. What if the vertex is on the x-axis, right? Then it's only going to cross the x-axis once, so it's going to have one x-intercept. And a sum, of course, will not cross the x-axis at all, right? Now, if the equation of a parabola is in standard form, y equals ax squared plus bx plus c, then we have an old friend, if you recall, the discriminant, which can tell us how many times the parabola will cross the x-axis. For parabolas that do not intersect the x-axis, each such point of intersection is called for the parabolas that do intersect the x-axis, each such point of intersection is called an x-intercept of the parabola. And to find the x-intercepts of any parabola, we simply set y equals 0 and solve for x. Now, here's how the discriminant can help us. Once you calculate the discriminant, if it's positive, you're going to have two x-intercepts, because the equation associated with setting this right part equal to 0 is going to have two roots. Remember? Two real roots. Now, at this point, we don't care about whether those are rational, irrational, all that. That's when we were solving quadratic equations, we were concerned with those things, right? But right now, we just want to know if they're real or not, because ax squared plus bx plus c equals 0 will have two real solutions when the discriminant is positive, so therefore you'll have two x-intercepts. If it's 0, that's when you're going to have just one x-intercept. And this equation, the associated equation where you set the ax squared plus bx plus c equal to 0, will have one real double solution. If it's negative, remember, you're going to have complex conjugate solutions. So no real x values that are going to be resulting from that scenario. So no x-intercepts. Those are the ones where either the parabola has a vertex off of the x-axis or one that never touches it, and also which will never touch it, like the ones I showed you in the beginning of this slide, okay? And that's how we find the intercepts. So here's a visual. Here we have parabolas that have two x-intercepts. Notice they cross the x-axis twice. This one as well, right? Here we have one x-intercept, right? Notice in that case, that means the vertex falls on the x-axis itself. And here are a couple of parabolas, this one and this one, that are never going to cross the x-axis, right? Remember, these are two different coordinate systems, so don't be saying, oh, this is going to cross that x-axis. No, this is the x-axis we're referring to with this graph, and this is x-axis when we're referring to that graph. And of course, neither one of those two are ever going to cross the x-axis, so such parabolas will not have any x-intercepts. So for this one, if you find the discriminant, it'll be positive. For this one, it'll be 0. For these, the discriminant will be negative. All right, so in this example, we're going to find all the intercepts of this quadratic function without graphing. So let me go ahead and replace f of x with y. So we get y equals x squared plus 5x plus 6. Remember, to get the one y-intercept, let x be 0, right? So we get y equals, that's going to 0 out, that's going to 0 out, so you get y equals 6, right? So the y-intercept of this parabola is 0, 6, okay? Now, to get the x-intercept, we let y be 0 and solve. So we get 0 equals x squared plus 5x plus 6. So we get 0 equals quantity x plus 3 times x plus 2. That's a simple factoring problem, right? First times first is first, last times last is last. Inner product and outer product give us the middle term when we add them, okay? So we get either x plus 3 equals 0, we're applying the 0 factor property, or x plus 2 equals 0. So we get either x equals negative 3 or x equals negative 2. So the x-intercepts are quantity negative 3, 0, and quantity, well, not quantity, I'm sorry. This is ordered pair. I've gotten stuck on that quantity business. Okay, so ordered pair negative 3, 0, and ordered pair negative 2, 0. Yeah, you don't want to say quantity here. We're not using parentheses in that sense, not in the computational sense, okay? So there are our y-intercepts. Now we're asked to verify the results with a discriminant check. So remember, here we have a equals 1, b equals 5, and c equals 6. So the discriminant, which is b squared minus 4ac, is going to be 5 squared minus 4 times 1 times 6, right? So it's going to be 25 minus 24, which is 1, which is greater than 0. So therefore, we expect it to have what? 2x intercepts, right? And we want to display the result on a graphing calculator as well. So let's take a minute to do that. Okay, so we have y equals x squared plus 5x plus 6. Okay, so we can indeed verify visually that this graph is going to have 2 x-intercepts at negative 3, 0 and negative 2, 0, as we've already verified. Okay, so there we have it. So please make sure that you know how to do this, and we will proceed. Now, we have already learned how to find the vertex of a parabola which is in standard form by taking that and equation and putting it into a vertex form. Now, if you recall, when we were solving quadratic equations by completing the square, it occurred to us at some point that, hey, why don't we just take the equation ax squared plus bx plus c equals 0 and go ahead and solve it by completing the square in a general form, and then see if we can come up with a formula to help us act more efficiently. And in fact, when we did that, we ended up with the quadratic formula. Now, when we do that here with y equals ax squared plus bx plus c instead of 0 equals ax squared plus bx plus c, what we will end up is with a nice shortcut, just as the quadratic formula is a shortcut to solving an equation by completing the square. We come up to a nice shortcut to having to put an equation of a parabola in standard form into the vertex form before finding the vertex. Okay, so here's the way we're going to handle it. We're going to take this equation y equals x squared plus bx plus c. This should look familiar to you if you remember how we derived the quadratic formula. And we're going to go ahead and complete the square. So remember, we're going to divide both sides by a. That's going to give us y over a equals x squared plus b over ax plus c over a. Now we're going to go ahead and complete the square on x squared plus b over ax. So we take 1/2 of b over a, which is b over 2a, and square it. And of course, we're going to immediately subtract the same expression. And don't forget, we have plus c over a from before. So we end up with y over a equals quantity x plus b over 2a squared minus b squared over 4a squared plus c over a, right? So we get y over a equals quantity x plus b over 2a squared minus b squared over 4a squared plus c over a. And now we're going to go ahead and find the common denominator, right? So that means we're going to have to multiply the top and bottom of this particular fraction by 4a, right? Because we want to get a denominator of 4a squared on this one as well. So we're basically doing this. So that's how we end up with 4ac over 4a squared, right? Now, instead of writing the negative b squared first, we can always write the 4ac first. So we get 4ac minus b squared over 4a squared. So we have, now we're going to go ahead and multiply the a back in. We're finished with what it was going to help us do, which is complete the square and all that. So we get y equals a times x plus b over 2a squared plus 4ac minus b squared over 4a. So if I write this as, my goal is to get it in this form, right? A times quantity x minus h squared plus k. So I want to write this as a difference, so I get x minus negative b over 2a squared plus whatever that expression is. I'm not really concerned about that, and I don't ever plan to memorize it. But this I'm interested in, because this tells me that this is my h, right? So the x value of my vertex is going to be negative b over 2a. Now, that's very handy to have. Now, remember, you don't need to memorize that. All you need is this. Why? Because once we have that, we're just going to plug it into the original equation to get whatever this is anyway, right? So there's no need to memorize that. But the moral of the story is that if you have y equals ax squared plus bx plus c, now that you've gone through all that and you've understood it, you can just use it. So that means the x value of your vertex is just going to be negative b over 2a. Okay? So let's see if we can put that to use. Being able to carry this kind of derivation on your own without any help is really what's going to separate the students that are going to make some real progress from students who will simply possibly pass the class but not make as much progress. So if you want to really expand your horizons when it comes to your mathematical journey, make sure that you take something like this and work it out on your own, okay? Because then you're going to reap the fruits from this point forward in your mathematical endeavors, okay? All right, so here we have a parabola, and we're going to find the vertex without putting it in vertex form, right? So remember, it is a standard form parabola. So we have a equals -1, b equals 5. Do I care what c is? Not really, because I know that the x value of the vertex is going to be -b/2a. There's no c in it, right? So we get -5/2 times -1. Now negative over negative is going to give me a positive, and that's just 5/2, right? So there's the x value of my vertex. So to get the y value of the vertex, that's just going to be f of that x value, right? So I get negative quantity 5/2 squared. I'm just plugging in the 5/2 for x in the original equation, right? Plus 5 times 5/2 plus 5. Okay, so we get -25/4. That negative is not being squared, so make sure that you don't turn it into a positive for no reason. And we get plus 25/2 plus 5/1, right? So the LCD is 4. No change is needed here because it's already 4, so we get -25 plus, here I need to multiply the 2 by 2, so I got to do the same on the top, and I need to multiply this 1 by 4 and do the same on the top, right? So we end up plus 50 and then plus 20. So we have 70 minus 25, right, which is 45/4, right? So the vertex of this parabola is at 5/2 45/4, just like that. All right, so there's another good one for you to practice, and then we'll proceed. All right, finally, we want to take a look at a few quadratic models today, okay? One of the classic quadratic problems has to do with upward projection. If air resistance is neglected, the height s in feet of an object projected directly upward from an initial height of s0 feet with initial velocity of v0 is given by s of t equals -16t squared plus v0t plus s0, where t is the number of seconds after the object is projected upward, right? Notice something interesting here, that the units work out so that you end up with distance units in all three of these expressions. So this is the acceleration of gravity right here. So the actual formula from physics is actually at squared plus v0t, 1/2 at squared, pardon me, plus v0t plus s0. So a is going to have units of, for example, here you're dealing with the English system, or the standard system as it's called. So here we get feet per square seconds, and time is being squared, so that's going to be in square seconds, plus velocity is going to be giving to you in as feet per second, and time is of course in seconds, and then the units of distance are feet. So notice here the second squares will cancel out, here the seconds will cancel out, and you end up with feet in all three terms. So You always want to make sure that when you're dealing with a formula that the units work out properly, okay? Again, this is more of a physics problem than usually dealt with in mathematics, but it's mathematical at the core. All right, so there is the formula. Now, of course, remember, if you were dealing with a metric system, you wouldn't have negative 16 here. You would have like negative 4.9, right? Half of 9.8, or negative in this case, because it'll be acting to pull it down. All right, so a ball is projected directly upward from an initial height of 49 feet with an initial velocity of 251 feet per second. Give the function that describes the height of the ball in terms of time t. Now, remember that we have s of t equals negative 16t squared plus v0t plus s0. So here we're going to have negative 16t squared. Now v0 here is 251 feet per second. That's speed, right? And the initial height is what we call S0, and here it's 49 feet, okay? So notice that we get negative 16t squared plus 251t plus S0, which is 49. So there is our displacement formula, or the formula that will give us the height at any time t. And then we want to know after how many seconds does the projectile reach its maximum height. Now, if you look at this quadratic equation, notice that it's going to describe an upside down parabola, right? The unhappy face. So it's one of these kinds of parabolas, correct? Notice that, of course, because of that 16, it's not going to quite look like that if this is drawn to scale. It's because the absolute value of negative 16 is a very large number, 16. It's going to be extremely narrow, right? But let's say that this is not drawn to scale, and for simplicity, I'm just drawing it like this. The whole point I'm making is that this is going to be an upside down parabola, right? So notice that at each time t, you have t, which is your horizontal axis, and s of t is your vertical axis. So at each point on this interval is representing a given time and the height of the projectile at that time. So notice that it's going to hit its maximum value, the maximum height, when you reach the vertex of this parabola, right? So what does it mean? It means we need to find the vertex of this parabola. So notice that you're focusing on this equation, right? Notice that A is negative 16, B is 251, make that, and C is 49, right? So therefore, I really didn't need C, but let's just write it, it's okay. So I know that here I'm not going to say the x value of the vertex, I'm going to say the t value of the vertex is going to be negative b over 2a, right? So it's going to be negative 251 over 2 times negative 16, right? So let's go ahead and compute that. All right, so we have, we know the two negatives are going to make a positive, so we just need to worry about 251 divided by 2 times 16, we know it's 32. So we get 7 point, say 7.84, right? Just to round things off. So basically, it's going to take 7.84 seconds for this projectile to reach its maximum height. What's going to happen to the height after that? It's going to start decreasing, right? Of course, remember, one thing that sometimes students are confused about, they think this is describing the path of the projectile. No, this is describing the height of the projectile. The path of the projectile is simple. You have something, you're throwing straight up from a height of 49 feet, and you're going to push it directly up. So this projectile is going to go straight up. It's going to reach its max height, and then it's going to what? Gravity is going to pull it back down. So it's going to go reach its max height, and then it's going to go drop straight back down. So this is not, and this function is not describing the path of the projectile. It's describing the what? The height of the projectile at any given time. Okay? So make sure you really understand that. All right. So they don't just want to know after how many seconds this happens. We already know the answer. So for the first part, after 7.84 seconds, but they also want to know what is the maximum height, right? So that's easy, because once we have the t, we just need to plug it into the s of t formula that we have here to get the maximum height. So we get s of 7.84 is going to be negative 16 times 7.84 squared plus 251 times 7.84 plus 49, okay? And we just go ahead and plug that in, and we'll get our value. All right, so we get negative 16 times 7.84 squared plus 251 times 7.84 plus 49. So there is the actual height after 7.84 seconds. We of course know this is going to be an approximate value because we're doing rounding, right? So 1033.39 feet. So a maximum height of approximately 1033.39 feet, which is reached, of course, after approximately 7.84 seconds. All right, let's see if there's a couple of other questions we can answer. All right, for what interval of time is the height of the ball greater than 501 feet? Now we know the height formula. Let's take a look at it quickly. Negative 16t squared plus 251t plus 49. Now we know we want this height to be greater than 501. So we're basically solving a quadratic inequality. So that means negative 16t squared plus 200 and, if you didn't have access to a calculator, this would have been a daunting problem, right? But with access to a calculator, it's as easily as one with super nice numbers, right? Because you're not going to be doing the hard work of, crunching these numbers, are you, right? So don't panic. So plus 251t. Now we're going to move the 501 to the other side. So let's bring up the trusted friend. So we get 49 minus 501, right? So minus 452 is greater than 0. Now remember, the way we solve quadratic inequalities is we go ahead and actually solve the corresponding equation where, so we solve negative 16t squared plus 251t minus 452 equals 0, and then that will give us the way the interval is going to be split up. Then we do test points. All of this was explained in a previous video, so please make sure you've viewed that. So here we have A is negative 16, B is 251, C is negative 452. So T is going to be negative B. We're just going to apply the quadratic formula, plus or minus square root of B squared minus 4AC over 2A. So we get negative 251 plus or minus square root of 251 squared minus 4 times negative 16 times negative 452, all over 2 times negative 16. All right, so we're going to actually type that in exactly as we see it. Let me clear all this. All right, so I'm going to start with a fraction line. I need to make sure that I get rid of that A and S because that's a result from the previous line. So I'm going to type exactly what I see. So negative 251, but without the plus or minus. I'm just going to put one of them in. So I'll put the plus in, okay? So now I go square root of 251 squared minus 4 times negative 16, and that's going to be times negative 452. I'm going to pause for a second, make sure I typed everything in correctly. Negative 251 plus 251 squared minus 4 times negative 16 times negative 452. You should definitely do that too. So now we're going to move down and put in negative 32. Okay, so we're going to hit enter. So that tells us, remember the plus case gave us, we're going to round, so 2.08. And now the beauty of these modern calculators, I can just double click that to copy it, and I'm just going to change that plus to a minus. This is a fantastic calculator and it's freely available. It's called HP Prime. It's almost, I don't think I've ever seen it not be available for any platform. So it's available on all platforms. Okay, so we're going to go change the plus to a minus now. So we get 13.61 approximately, right? So let's change that to a approximately, right? So the minus case gives us 13.61. All right, so remember, we're solving an inequality. So we're going to draw our number line. We're going to put the two values we just found. Those are the places where the polynomial is 0. So 2.08 and 13.61. Now we're going to do some test points in each of these regions. So we know that at these points, the value of the polynomial is 0. Now, to the left of 2.08, you don't have to go far. How about t equals 1 or 2, whatever? So let's test t equals 1. That's as good a value as any. Between 2.08 and 13.61, let's just go ahead and test 5, for example. That's the test point. And we'll do a test point for greater than 13.61. How about 15? All right, so here we're going to go ahead and plug in 1 in here so for t. So we get negative 16. I'm not even going to bother going times 1 squared because I know 1 squared is 1 times negative 16 is negative 16 plus 251 times 1, which is just plus 251, and then remember we're in this equation, right? Be very careful not to go there. You're right here. Focus on this. And then 251 times 1 is 251 minus 452. So all I care about is the fact that the sign is going to be negative, okay? Now I test 5, so I'm just going to say negative 16 times 5 squared plus 251 times 5 minus 452. It's positive. And now I'm going to plug in 15. So I'm actually going to copy that. And I'm just going to change every 5 to 15. Now you may wonder why this 2 isn't outside the parentheses. It could be. In this case, it doesn't make any difference, right? So I can just leave it in there. And I get a negative value. So notice the only time when this inequality is satisfied is between 2.08 and 13.61. At all other times, that inequality is negative, right? So for what interval of time is the height of the ball greater than 501 feet? For this interval, from 2.08 to 13.61, just like that. All right. And finally, we want to know after how many seconds will the ball hit the ground. Now, that one is, of course, easy because it's going to hit the ground when the functional value, negative 16t squared plus 251t plus 49 is equal to what? 0. That's where the ground is, right? So you want the height to be 0. All right, so assuming that here's the building, right? The projectile is moving up, coming down. Somehow it's going to clear the building and keep going until it hits the ground somewhere down here. Remember, that's 49 feet, okay? So somehow on the way down, it's not going to get stuck to that building, and it's going to go all the way down to the ground, okay? So now all we got to do is we got to solve this quadratic equation. So A is negative 16, B is 251, and C is 49. So we get T equals negative B. I have the quadratics here, so I'm not going to write it again. I always recommend that when you're going to use a formula, any formula, write the full formula down first, then start substituting, because then you're much less likely to make a mistake. So we get t equals negative 251 plus or minus the square root of 251 squared minus 4 times negative 16 times 49 over 2 times a, which is 2 times negative 16. So again, we're just going to type it into the calculator just like we see it. All right. Now I notice I have something similar to that here already. I'm just going to copy that. I'm going to change whatever I need to change. So minus 4 times negative 16. I need to change that negative 452 to 49. That's it. Everything else is the same. So I get approximately 15.88 seconds. Now we need to figure out what the plus case gives us. That's the minus case we just figured out. So, or negative 0.19 seconds. Of course, we can't have time being negative, so the only possibility is right there. This one we reject. Okay? So basically this ball, or this projectile, whatever it may be, well, it's a ball in this case. So it's going to take about 15.88 seconds after it's projected upward to hit the ground. I guess you can think of that's why it can just roll off of here quickly and go, because it's round. All right, so that's how you do that one. Make sure you can handle that, and we'll proceed. All right, for our next problem, we have a piece of cardboard right there, the entire piece, which is 3.5 times as long as it is wide. It is to be made into a box with an open top by cutting 3-inch squares from each corner. So you cut a square from each of these corners, right? And you fold these up, these 4 parts. And what do you end up with? A box, right? Let x represent the width of the original box. So it's from here all the way to here, okay? And now we want to answer the following. Represent the length of the original piece of cardboard in terms of x. So look, from here to here, it's x. Now we know that the length is 3.5 that. So the length here, this is the width, right? So the length is going to be 3.5x. State the restrictions on x and what will be the dimensions of the bottom rectangular base. So this part. We want to know the dimensions of this base and what are the restrictions on x. Well, look, whatever x is, you have to be able to take 6 away from it, right? So because 3 from here, 3 from there. So this x minus 6 can't be negative, right? So it has to be greater than 0. So x definitely should be greater than what? Than 6. Now, as for the dimensions, remember, from here to here is x, right? Which is the same as from here to here. What are we taking away? 1, 3, and then another 3. So basically, this part here is x minus 6. And I know from here to here, the entire length of the original cardboard is 3.5x, and I'm going to take away 2 3s from that as well. So the length of that inner rectangle, which is going to become the base, is going to be 3.5x minus 6, right? So it's going to be, usually we say the dimensions length by width, right? So it's good, the dimensions will be 3.5x minus 6 by x minus 6, and those are both, of course, in inches. So you have to parenthesize because the inch needs to be applied to each of these terms, right? So make sure that you parenthesize when you're going to describe it like that. All right, let's see what other questions we need to answer. All right, so it's the same problem, so this is just repeated. Now we want to find the function v that represents the volume of this box, right? Now remember, once this box is folded up, the sides of the box or the rectangular solid are going to be x minus 6 by 3.5x minus 6, and then the height of the box is going to be what? The 3. Remember, this part, this part, this part, and this part are going to get folded, right? So that creates a height of what? 3 inches, right? So the volume, of course, is length times width times height. So you're going to get length, which is 3.5x minus 6 times width, which is x minus 6 times height, which is 3. So if we multiply that out, we get 3.5x squared minus let's go ahead and bring our trusted friends. So we have 3.5 times 6. So minus 21. Now we're going to distribute. We just distributed the 3.5x. Now we're going to distribute the negative 6. So we get minus 6x plus 36, right? Don't forget, all of that is going to get multiplied by 3, which I will write on this side just because it looks a little bit easier. All right, so we get 3 times 3.5x squared minus 27x plus 36. So finally, okay, I'm going to do the shrinking job again real quickly. All right, so finally we get v, and notice that it is going to be just a function of x, right? So we get v of x equals 3 times 3.5, I believe that's 10.5, but let's make sure. Yeah, it is. Okay, so 10.5 x squared minus, that should be 81. 3 times 20 is 60. 3 times 7 is 21. So minus 81x. 3 times 36. 3 times 30 is 90. 3 times 6 is 18. So 108. So plus 108. So there's our formula for the volume function. For what dimensions of the bottom of the box will the volume be 520 inches? So basically we want the volume formula 10.5 x squared minus 81x plus 108. We want that volume to be 520. That's all. So we just need to solve that for x, and then we can find the dimensions really easily. Okay, so so we have 10.5 x squared minus 81x. So I need to do 108 minus 520. So negative 412 equals 0. So I have A equals 10.5, B equals negative 81, C equals negative 412. So now we get X equals negative B plus or minus square root of B squared minus 4AC over 2A. So we get the opposite of B, that's going to be the opposite of negative 81, so it's 81, plus or minus square root of B squared, so quantity negative 81 squared minus 4 times 10.5 times negative 412, all over 2 times 10.5. So let's go ahead and enter it as we see it. Remember, I start with that, and then I go to make sure I get rid of that A and S on the top. And replace it with 81. I'll do the plus case first. Plus shift square root of quantity. Now it doesn't matter whether I square 84 or negative 84, so I'm just going to put 84, and then squared minus 4 times 10.5 times negative 412. Now we go downstairs and we put 21. 2 times 10.5, right? 21. All right. So we get 11 point, approximately 11.29 inches, or so we get X is that, or X is, now let's change to the minus case. Negative 3.58. Now obviously we can't have a negative X value, because remember what X is. X is this length of this width of the original cardboard piece. So therefore that's the only possible answer. So the answer is 11.29 inches. All right, finally, find the values of X for such a box to have a volume between 600 and 800 inches. All right, so basically this is the scenario, right? We want to solve this particular inequality. So here's the volume formula right there, right? So we want 10.5 x squared minus 81x plus 108 to be between 600 and 800, like that. You see? So there are two inequalities we need to solve. One is 600 is less than 10.5 x squared minus 81x plus 108. And the other one is 10.5 x squared minus 81x plus 108 is less than 800. Okay, so we already know how to solve these. Remember, we did one already, okay, earlier today. So this time what I want to do is I want to show you a nice graphic trick, okay? We're going to solve this on a graphing calculator. So I'm going to show you a graphical method to solve something like that, because I did tell you I'm going to make you technologically aware. All right, so here we go. Let's go ahead and bring up Desmos again. And I'm going to clear that. I'm going to type our equation. So just give me a minute to transfer that over. I'll be right back. Okay, so here are our two inequalities. One was 600 is less than 10.5x squared minus 81x plus 108. So the volume is greater than 600. If you read it from right to left, it'll be greater than. Remember, the inequality symbol opens toward the larger expression or value. And then the other inequality is this one. So first I graphed the top one, right? So notice the top part of this parabola is shaded. Now the summit, or the not the summit, what do we call it? The vertex is really high and off the image right here, but we don't need it, because basically when we graph this other one, we're going to see this other one is in blue. So now what you see in purple is the solution of the system consisting of these two inequalities, okay? So now we have two sets of x values within that solution region. One which is not of use to us because those are negative values of x, and we can't have negative values because x represents the width of a piece of cardboard, right? So these two values, these two x values, are the ones we're interested in. So if we just mark them, we can answer the question. So the two x values are 11.71 and 12.85 approximately. And that's the way that we solve this one graphically. So basically we say for x belonging to this interval, 11.71, I believe it was. Yeah, 71 and 12.85. And that's all there's to it. That's how you solve that one, okay? So again, yeah, are these more challenging problems than what you would find in an algebra book? But of course, otherwise the class would be called algebra, wouldn't it? So we're expanding our horizons, but you can do this. Trust me, you can do this. It's just a matter of hanging in there, and if you don't get it at first, try again until you get it. You know, as I said, there's plenty of help options available on systems like my MATLAB, but don't jump to them. The best option is to try to get to the answer on your own. You know, on a few problems you may spend hours, but then you're going to open channels in your mind that are going to help you get to answers quickly from that point forward. So in other words, you're gaining depth in mathematics, and that depth is going to provide for much easier sailing the rest of the way. All right, here's a graphic problem. We're given the graph of a parabola, well, part of a parabola, and we're asked to find the equation of the quadratic function that could be whose graph could be this parabola. Okay, so it's a lot easier than it appears at first. You're like, wow, how do I do that? Well, remember, a parabola in vertex form, and that's the magic thing here because we have the vertex. And we know that a parabola in vertex form has the form y equals a times x minus h squared plus k, right? So I'm going to use both of those points. I'll use 0, 0 as my particular xy that I'm going to use at this point, and I know what h and k are. So I'm going to plug in y equals 0. So use y equals 0, x equals 0, h equals 7, k equals -7 to find a. That's what we're going to do. So we get 0 equals a times 0 minus, we know that h is 7 squared, plus k, which is -7. So I get 0 equals, now this is going to be -7, and when it's squared, it'll become 49. So 0 equals 49a minus 7. So I get 7 equals 49a. So a equals what? 7 over 49, or 1/7. So now I'm ready to write the equation of the quadratic function. F of x equals a, which is 1/7, times x minus h, which is 7, squared, plus -7, which I can just write as what? -7. There you go. That's how you would handle a problem like that. All right. Here's one last one for the road, right? The total amount spent by some number of people on clothing and footwear in the year 2000 to 2009 can be modeled by the quadratic function f of x equals this expression right here, where x equals 0 represents January 1st, 2000, x equals 1 represents January 1, 2001, and so on. And f of x is in billions of dollars. According to the model, in what year during this period was the amount spent on clothing and footwear a maximum? Now, you should be able to answer this. You should definitely pause and try to answer this on your own, because we've done a similar problem already. So please do so. All right. So you know that this is going to be a what? Because a is negative, it's going to be one of these parabolas, right? So that means the vertex is going to represent the maximum functional value, right? So all we got to do is what? Find the vertex. So the x value associated with the vertex is what we're going to need to figure out the year, right? So a is -4.973 and b is 71.23. And the x value of the vertex is going to be -b over 2a. So it's going to be -71.23 over 2 times -4.973. The two negatives are going to make a positive, so we just need to worry about the values. So 71.23 divided by 2 times 4.973. So we get approximately 7.16. All right. So remember that what x represents, right? All right. So first of all, it represents the number of years since January 1st, 2000. That's basically what it represents, right? Because x equals 0 represents 2000, January 1st, 2000. And now all we need to do is add 7 to 2000, right? So basically the maximum is going to occur in the year 2007. And they want to know also what if they also ask you for the actual amount that was spent? Would you be able to do it? Well, that's really easy, right? That's just f of whatever we had, 7.16. So you just plug in -4.973 times 7.16 squared plus 71.23 times 7.16 plus 96.27. All right, so let's go ahead and compute that. So negative 4.973 times 7.16 squared plus 71.23 times 7.16 plus 91.27. Always double check, make sure you've plugged it in correctly. Negative 4.973 times 7.16 squared plus 71.23 times 7.16 plus 92.9. Ooh, there it is. See why you always have to check? That's 96.27. Okay? Now we hit enter. So 351, approximately 351.33. Now keep in mind, that's in billions of dollars. So we say that many, to present our solution, we'll put a dollar sign and then we'll put a billion afterwards, like that. Okay? All right, so you can see how important and useful quadratic functions can be. So please make sure you understand this entire video before attempting any homework problems, and that should do it for this video. You take care until the next time.